Modern enterprise environments operate as massive systems of systems, where thousands of technical nodes must align with precise business intents to avoid systemic collapse. Applying a traditional one-off design methodology to this complexity makes late-stage failure a mathematical certainty. The variables simply move too fast for a single snapshot to capture. This exposes the water fallacy, the assumption that architecture is merely a preliminary design phase, a static document completed before handing the project off to development. A static architecture cannot survive dynamic system complexity. Managing these environments requires a different engineering logic. The ISO 42020 standard provides that logic, a rigorous framework designed to govern extreme architectural complexity. This standard treats architecture as an active, continuous engine, rather than a static document. The engine is powered by three foundational core processes: Clause 8, Conceptualization, Clause 9, Evaluation, and Clause 10, Elaboration. They are linked by glowing bidirectional feedback loops. By utilizing this closed-loop mechanism, abstract stakeholder concerns are compiled into execution-ready digital threads. Clause 8, Conceptualization, is the first chamber of the engine, operating at the highest level of abstraction. The process begins by capturing chaotic stakeholder concerns. A business lead might demand zero downtime, while compliance requires strict data sovereignty, and finance sets a hard budget cap. These philosophical concerns are translated into a strictly bounded problem space. This boundary prevents the engineering team from wasting resources solving the wrong problem. In the solution space, engineers systematically synthesize available technologies to address that problem, creating multiple alternatives to avoid the bias of favoring a single favorite solution. We compare alternatives within the trade space. Here, we plot active-active redundancy against infrastructure cost. Visualizing these trade-offs forces stakeholders to negotiate based on data to identify the optimal mathematical balance. Once a point on the curve is locked, it defines the candidate architecture. Conceptualization replaces subjective guesswork with mathematical boundaries, narrowing the architectural choices before hard engineering begins. The candidate architecture then moves into Clause 9, Architecture Evaluation. The standard mandates that technical metrics are not measured in isolation. They must be proven suitable against the business context. This validation uses a dual-axis filter with two dials: architectural analysis on the left and value assessment on the right. Architectural analysis measures structural facts like network latency and module coupling. Value assessment interprets those facts against the stakeholder's original utility requirements. This prevents misalignment. A system with microsecond latency provides no value if the primary stakeholder concern was actually global data sovereignty. This chart shows the value function, the mathematical bridge connecting the two axes. It maps a technical metric, like 99.999% uptime, directly to a verified business utility score. Evaluation acts as a filter, translating raw technical facts into verified business utility. This evaluation is a continuous iterative process, moving away from the linear waterfall model. If a candidate architecture breaches a defined threshold during the evaluation, it triggers the engine's regulatory feedback loops. If a strategic failure is identified, a backward loop fires a data packet to Clause 8, shifting the tradespace graph to force recalibration. If viable but lacking detail, a forward feedback loop fires to Clause 10, demanding higher resolution models. This bidirectional closed-loop system is the primary regulatory mechanism of the standard. It identifies design flaws early to prevent catastrophic failures during implementation. Once evaluated, the candidate architecture enters the final node, Clause 10, Elaboration. The objective is to shift the intangible architectural concept into a tangible, implementation-ready architecture description. Because no single diagram can explain a complex system, it must be dissected into viewpoints. Each one addresses the specific concerns of different stakeholders, from security officers to database administrators. We visualize this dissection as discrete architectural views. The architecture is sliced into layers: a security view, a database view, and a business logic view. However, having different engineering teams work on isolated views creates a risk of logical contradictions. To prevent this, the standard requires a metamodel. A glowing grid materializes underneath, projecting vertical lines that snap components across the security, database, and business logic views into perfect alignment. This grid enforces consistency, serving as the digital thread holding the architecture description together. Elaboration validates the structural integrity of the blueprint, resolving contradictions before any code is written. The complete ISO 42020 engine operates as a unified system. Raw concerns enter Clause 8, pass through the dual-axis evaluation of Clause 9, and crystallize into grid-aligned blueprints in Clause 10. By utilizing mathematical trade-offs and utility functions, this framework replaces subjective design decisions with a traceable engineering record. The continuous feedback loop removes the bias of favoring a single solution, which is a frequent cause of failure in complex builds. Every technical model delivered through this process is explicitly tethered to a mathematically verified business value. The result is a system capable of immense scale and seamless interoperability, where every component has a verified reason for existing. When managing systems of systems, organizations cannot rely on guessing at a final design. They require an engine capable of systematically discovering it.